Okay, so here is a continuation of the other video. Here, again, we have the same car that starts at rest. It accelerates at 3 meters per second square for a time of 5 seconds to the right of the screen. And here, I've asked 6 different parts just to show you how to play with these kinematics equations and how to handle different situations based on the time interval given. Okay, all right, so if you need to, again, pause the video, read the different parts. This way, you know how to attack these types of problems. All right, let's knock out part A. So part A asks you to find the average speed between 0 to 2 seconds, which is the first 2 seconds. So we can just apply the average speed definition in physics. Average speed is simply the total distance divided by the total time. Here, in this particular part, the time is given as 2 seconds because it wants us to go from 0 to 2 seconds. So in order to do so, we need to know the distance. Well, this is the variable that's holding us back in order for us to complete finding average speed. But that's okay. You'll have to recognize again that in this particular scenario, the car is going to accelerate to the right of the screen from rest, so it will never turn around. Because it doesn't turn around, it's moving in one direction. So therefore, the distance is the same as the magnitude of your displacement. So that's an important key to kind of keep in mind as you practice in finding these values. That's important because in order to find d, I can use my displacement function. Again, my displacement function will allow me to find the magnitude, aka the distance traveled without needing to include the direction. Here, I wrote out the displacement function, which is VIT plus 1/2 AT squared. We can cross VI out for this particular problem because it starts at rest. So therefore, the displacement function is simply 1/2 AT squared, A being 3 meters per second squared. Time here for this part is 2 seconds because it's from 0 to 2 seconds, which is a difference of 2 seconds. Okay, don't forget about the square. And if you do all that, you should get a answer of 6 meters. Well, this is your magnitude of the displacement. So the question is asking for average speed. So here we found how far it moved to the right. So really the distance is also 6. Again, distance is equal to the magnitude of your displacement, aka leave out the direction. So it's just 6 meters. So we just found the distance. All we have to do is substitute it back into the original function of average speed. Average speed is total distance divided by total time. We now know the total distance is 6. We know the time already is 2 seconds. So therefore, 6 divided by 2 is simply 3 meters per second. Average speed, again, is a scalar quantity, so you don't need to include direction. So that's it. Your answer is simply 3 meters per second. So the average is about 3 meters per second during the first 2 seconds, okay? All right, let's do part A using a different strategy. Well, average speed is the magnitude of average velocity if the object moves in one direction, which it is in this scenario. So you have to recognize that even though the question uses the phrase average speed, you really is asking you to find the average velocity and just leave out the direction at the very, very end. So here, because I know that the object moves one way, the average velocity function for an object doing so can also be calculated by using VF plus VI divided by 2. Well, here, it's important for you to write these velocities out. Once you're given A, it's super easy to write out the velocity at each time. Here to the top of the screen, I have V equal 0 second. Well, at times you go to 0, the object's at rest, so the velocity is just 0. At 1 second, it increases by 3 because that's what the acceleration value is. So it's important for you to learn to interpret this acceleration value. It says the object increases its speed or velocity at a rate of 3 meters every second, hence 3 meters per second squared. So 1 second later, the new speed is 3. Another second has gone by, the car has sped up to a velocity of 6 meters per second or plus 6 meters per second. Another second has gone by, it'll increase another 3 and so on and so on, okay? But here, I can just stop at 0 and 2 because part A has to do with 0 and 2 seconds. So here, I can just plug values in. I want to select values at 0 and 2 seconds because that's what the question is relating to. At times we go to 0, my velocity is 0. At times we go to 2, my velocity is plus 6 meters per second. And I can just plug values in. VF is 6, VI is 0. 6 plus 0 is just 6. 6 divided by 2, that's just simply 3. Again, that will show you that the average velocity is 3 meters per second east. However, this is just to show you how to find average speed, because the magnitude, which is 3 meters per second, is the same as your average speed. So really, you see the number itself is the same. Okay. All right. So that's that. So that's part A. Let's do part B. Part B asks you to find the average velocity between 0 to 3 seconds. So here I notice that I use the term average velocity, which is a vector. So I do need to find the speed, or the average speed, and give it a direction as well. All right. So let's do it. I'll do this a couple different ways for you. To find average velocity is simply displacement divided by time. And then to find our displacement, which is what we'll need, we'll have to use the displacement function. Here, I just went ahead and substituted in t as 3 seconds because the problem said so. From 0 to 3, that's 3 seconds. The only thing holding me back is my numerator, which is my displacement. But that's easy to do. My displacement is simply VIT plus 1/2 AT squared. This is your position function. Therefore, I can cross out VI for this one because it starts at 0 second. So it's important that you just don't cross VI out because the problem starts at 0 meters per second. I cross VI out because this particular part starts at 0 second, which brings me back to the very, very beginning of the problem, which shows that VI is indeed 0. So I can cross that out. Okay. So don't just cross it out just because I'm doing it here. Make sure to pay attention to where the time starts. All right. Therefore, that reduces down to just 1/2 AT squared, and 1/2 is there, A is 3, and then here the t is 3 seconds. Don't forget about the square, and if you do that, you should get a displacement of 13.5 meters to the right. But here we're just doing calculator work, so I'm just going to plug in 13.5 for my delta x, and therefore V average now is simply 13.5 meters divided by 3 seconds. And if you reduce on your calculator, you should get approximately an average speed of 4.5 meters per second. And then since it asks for average velocity, we'll go ahead and give the average speed plus the direction here, which is east. Okay, so average velocity needs to have a direction. In this case, it's 4.5 meters to the right, aka east. All right, so that's the answer to that. Now, you can also, again, use the same strategy as previous part A, but notice here, the time interval is between 0 to 3 seconds. So all you have to do is write out all your velocities from 0 to 3, and then use the values from 0 and 3. Okay, so VF in this case would be 9 meters per second. VI would be 0 because that's the interval of time that the question is asking. So 0 and 3 seconds, those are my 2 points that I need. Therefore, VF is 9 meters per second. VI is 0. And then so 9 plus 0 is 9. 9 divided by 2 is 4.5. And you see that it has the same magnitude of 4.5 meters per second. But because it asks for average velocity, I will go ahead and be proper and just write east as well. That's the direction. All right. So as you can see, whichever strategy works best for you, apply it. Part C. It asks you to find average speed between 1 to 5 seconds. Okay. It's important, again, to pay attention to the interval 1 to 5 seconds. So let's go ahead and place all of our values here for instantaneous velocity. Okay. Here, 0 second is 0. Every second, the velocity increases by 3 because the acceleration is 3 meters per second. So every second, the velocity increases by 3. So it goes from 0 to 3, 3 to 6, 6 to 9, 9 to 12, 12 to 15. All right. So therefore, we can just use the same strategies as in part A. The average speed is distance over time. We know that the time is 4 seconds because from 1 to 5 is 4 seconds. We don't know what D is. But again, because the car is moving in one direction, it hasn't turned around, or in this case, it will never turn around. We can just go ahead and plug values in. Here though, because time is 1 to 5 seconds, my VI here, I cannot cross out. Okay. So hopefully if you listen carefully in part B, I did say that you cannot just cross out VI because the diagram has a VI at 0. You have to pay attention to where the problem starts. This particular part starts at 1 and it ends at 5 seconds. So at 1 second, the car is already moving. Well, how fast is it moving? It's moving at a rate of 3 meters per second because it's already in motion. So therefore, VI in this particular problem is 3, and that value is taken to the right of my to the top of my screen there. At 1 second, it's already moving at 3. time, well, what's the time? The time is 4 seconds because the interval here is from 1 to 5. So that's why my t is 4 seconds. All right. Other than that, a is 3, and then again, time is 4. Don't forget to square. And then if you square all that, you get 12 plus 24, and then 12 plus 24 is 36. And then 36 meters is your distance. All right, so we just plug 36 into D, and then so average speed is 36 meters divided by 4 seconds, which will give us an answer of 9 meters per second. Okay, now we can find average speed by using the average velocity for this particular problem because it hasn't turned around. So therefore, average velocity will give you the magnitude, aka the average speed. So we can do VF plus VI divided by 2. And again, the 2 points being assessed in this particular problem is 1 second to 5 seconds. So hopefully if you're doing this on your own scratch paper, highlight your start point and your end point. This way you're not, plugging wrong values. Here at 1 second, it's already moving at a rate of 3 meters per second. At 5 seconds, it's moving at a rate of 15 meters per second. So my VF is 15, my VI is 3. Okay, so you notice here in this part, I'm not crossing out VI because I'm not starting at 0 second, I'm starting at 1 second. So therefore 15 plus 3 is 18, 18 divided by 2 is 9, and that's your answer. As you can see, the magnitude is the same. The magnitude is 9 meters per second. And average speed is a scalar, so I don't need to include direction. So that's the second way to do it. All right, so pick a strategy that works best in your brain and utilize it. All right, let's do part D. Part D asks you to find average velocity between 4 to 5. This is very similar to part B. So if you don't understand part B, rewind the video and watch part B again. All right, so average velocity is displacement over time. In this case, I know the time is 1 second because from 4 to 5 is only 1 second, and delta x is what's missing. Well, I can use my displacement function or precision function again. Here, I want to remind you that the problem here starts at 4 seconds and it ends at 5. So therefore, you cannot cross out the VI term. Okay, you can't not cross it out because it starts at 4 seconds. All right, so here I've highlighted it times equal to 4. That's my initial. Okay, so at 4 seconds, the object is already moving at a rate of 12 meters per second. So for the initial velocity, I will plug in 12 meters per second because that's what it is at 4 seconds, which is my starting point for this part. The time is 1 because from 4 to 5 is 1 second. A is given in the problem as 3 again. And then here, t to the right side of the function is 1. And then if you do the math carefully, your delta x is going to be 13.5 east. But here we'll just use the number for the calculation purpose. And therefore, on the left side here, V average is equal to displacement over 1 second. My displacement I just found is 13.5. So therefore, it's just 13.5 meters divided by 1 second. So the answer is going to be 13.5 meters per second. And I want to include the direction for this particular part because it asks for average velocity, which is a vector. Okay, and I don't see the word magnitude being used, so I want to go ahead and include the direction. Again, you can write to the right or you can use the plus sign if you like. All right, we can do the same strategies as we've done the first few parts. In this case, we can use the average velocity function when acceleration is constant, which it is in this case, which is just Vf plus Vi divided by 2. The time to start is at 4. The time that ends is at 5 seconds. So I want to highlight these 2 points again. So hopefully as you're practicing, do what I'm doing now on my screen. Highlight the interval of time that you're interested in so you plug in the right values for the functions. So these kinematics equations are not that bad. You know, it's only difficult for kids, I think, who are sloppy with starting point and ending point. So here, my Vf is at 5 seconds. My Vi is at 4 seconds. So I'm going to use Vf as 15 meters per second. And then Vi is 12 meters per second. So therefore, I'm going to plug it in, 15 meters per second plus 12 meters per second. And if you do that correctly, you get 27 meters per second over 2. And 2 is just part of the function. That's how you find averages, you know, when the change is a constant rate. All right, so therefore 27 divided by 2 reduces down to the same value of 13.5 meters per second. And there's the direction for you in yellow because it asks for average velocity. All right, part E and F on this slide. E asks for the time to cover the first 20 meters. Okay, so this one's a little harder, so hopefully watch this one carefully. In order to find the time, I can use my displacement function. Here, I can cross out VI because it asks for to cover the first 20 meters. So therefore, it starts at 0 and it's just going to go 20 meters. How much time would that take? That's okay. We know delta x, we know a, so the only thing missing here is our t. Well, delta x is going to be 20. Again, I'm going to leave the plus sign out because plus 20 and 20 in terms of calculation is the same quantity, so there's no need to write a plus sign here. 1/2, a is 3, and then I can reduce 1/2 and 3 down to 1.5, right? So 3 times, 1 times 3 is 3, 3 divided by 2 is 1.5, there's that. And then to get t squared by itself, you need to divide both sides by 1.5. By doing so, you get t squared. But then to get t by itself, you need to square root. Okay, this is t squared. So therefore, 20 divided by 1.5 is 13.33. But then to get t by itself, you need to radical both sides, which will give us t. So therefore, the square root of 13.33 will give us an answer of about 3.65 seconds. So that's our answer. So if I just lost you in terms of algebra there, you want to go back and listen to that. Okay, so get rid of t, get rid of the square term by radicaling both sides, if I can speak. All right. Now, the other strategy to use it is to use your average velocity functions. Average velocity, when a is constant, is delta x over delta t, which also equals to vf plus vi divided by 2. And these are two functions we played in the last 4 or 5 parts. Now we just set them equal to each other because they represent v average. Well, the question asks to find time, but I notice here time is in my denominator. So I'm going to flip the whole function upside down, left and right side, just to get delta t in the numerator, because that's what I'm trying to find. So anytime your variable that you're asked to solve for is in the denominator, I like to flip it when appropriate. In this case, it is appropriate. So therefore, delta t over delta x is equal to 2 divided by vf plus vi. But I notice here delta t is not by itself yet. So to get delta t by itself, I have to get rid of this delta x in the denominator. Well, I can just multiply both sides by delta x, and that'll give me delta t by itself. Here I've chosen to use parentheses just for good habits. Okay, so here I'm going to cross out vi because vi is 0. Vi is 0 because, again, you're trying to find time it takes to cover the first 20 meters, which it implies that you start at 0. And therefore, delta x is 20 because that's given in the statement. But here you notice I don't know what the final velocity is. Like, if you watch my cursor, it's going to accelerate and it's going to gain speed, it's going to gain speed, it's going to gain more speed. So by the time it gets to the 20 meter mark, how fast is it going? I don't know. It's not given to you directly. Because it's not given to you, you have to go figure it out, okay? Well, I can use this kinematics equation. That doesn't require time. Well, why would I want to use this one? It has a VF in it, and it has an A, and it has a delta X, which are quantities that are already given to you. Here, VI is 0. I know my A, which is 3. I know my delta X, which is 20. By doing so, it tells me how fast the object is moving at that position, 20 meters down the road. Here, it's just plug and chug. Okay, A is 3. Delta x is 20. So if you do all this, you'll get VF square is equal to 120. But this is VF square. You need just VF. So therefore, to get VF by itself, you radical the left side and you also radical the right side. So the radical of VF square cancels out with the square term, leaves us with VF. And therefore, square root of 120 is VF. And if you simplify it in your calculator, the velocity at the 20 meter mark is about 10.95. So by the time it reaches a distance of 20 meters down the road, it is moving at a speed of 10.95 meters per second. Well, we just found what VF is. Okay, so now it's just kind of plug and chug. The only thing holding us back was VF here. Now we just found VF, so really it's 2 divided by 10.95 times 20. And that simplifies on your calculator to be equal to 40 divided by 10.95. 2 times 20 is 40, and then 40 divided by 10.95 will give you an answer of 3.65, which is the same answer we got using the position function or your displacement function on the left side there. Okay. All right, part F. Part F is super whack. It has to find time required to accelerate from 5 meters per second to 17 meters per second. It gives you VI, it gives you VF. We know A, so the only thing that's missing is T. So here, I'm just going to use my average acceleration equation because I have a lot of the information already. I'm going to go ahead and solve for delta T. Delta t here is in the numerator. Multiply both sides by delta t and then divide both sides by a. So delta t is going to equal to delta v over a. Or in this subfunction here, just switch the placement of t and a because you're not adding anything. So move the delta t up to the left side, move a down into the denominator on the right side, which is what I have here. Delta v is just vf minus vi over a, and therefore time is simply equal to vf, which is 17, which is given. The initial, which is given, is 5. Your acceleration in the problem has been 3 meters per second squared. So therefore, 17 minus 5 is 12, and then 12 divided by 3, which is 4 seconds. So it would take the car about 4 seconds to accelerate from 5 meters per second to a velocity of 17 meters per second. Okay, so the goal of this particular video and future videos is to show you guys how to play with these kinematics equation and how to apply them properly based on initial and final condition givens to you in these different parts. All right, I hope that helps. Stay nerdy, don't be whack.